Good morning, everybody. Welcome to today's webinar. Thank you for joining us. Today, of course, is the second webinar in our Sterile Barrier Systems webinar series, which we are hosting every Thursday from 11 in the morning. This webinar is brought to you compliments of SafMed. SafMed has been your solutions partner for over 30 years now, both in the theatre and in the CSSD environment. Today, as we said, is webinar 2 in our series relating to sterile barrier systems. Next week will be webinar 3. Next week, of course, is also our Africa Health Congress. The CSSD leg of it will be hosted on Wednesday, the 27th. And our last webinar in this series will be on the 4th of November. Hopefully, you'll be able to join us for the remaining webinars. In today's session, we're going to cover some information that I've honestly never heard presented before in local or international webinars. I'm hoping to bring you information that is new, that is challenging, and that is pertinent to what it is that we do. So today we're going to really take a good look at how sterile barrier systems are actually made, how they're manufactured, what standards they need to comply with, the actual test methods used in the laboratory setting to make sure that they do indeed comply. We'll look at interesting stuff like a germ proofness test. And we'll touch on that touchy subject of standard cotton linen and its use as a sterile barrier system, something that is quite common in the South African setting and in fact in Africa as a whole. In our first webinar, which hopefully you've also received a link to, if you were unable to attend it, you missed it because you were busy, you'll be able to view that video or recording of that first webinar. And in that, we reminded ourselves that sterile barrier systems can be defined or divided into different types. And of course, there is the wrap type materials, there are pre-formed materials, and there are reusable type materials. In the South African setting, both in the CSSDs and within the hospital environment itself, we will find a variety of devices packed in, again, a whole series of types of sterile barrier systems. Generally, we'll see sets and instrument trays packed in wrapping materials. We'll see all sorts of single items packed into plastic paper reels or plastic paper pouches, paper bags used very commonly in the South African setting, and containers, of course. Single-use wraps can be made of a variety of materials, and that includes crepe paper, so it's paper-based, wet-laid non-wovens, and SMS materials. Those are all materials available in the South African setting and used quite commonly in our hospitals currently. So this may be something you had not seen before, and that's the actual process of making, in particular, a non-woven sterile barrier system. An example of that would be like an SMS material. And the very beginning of the process is actually creating the web or creating the materials that are needed to make this web and the actual formation thereof. And there are a whole series of methods that are listed over there, as you can see. The ones that are more familiar to us, the ones that are used in the products that we know about in the South African setting, include the wet laid methodology, the spun laid, the melt blown. Those are very familiar to us. Once we've created a web, and I'll show you a graphic of that shortly, we now need to bond all of those materials together. And there are three main methods of bonding, and that includes a thermal bond, a mechanical bond, and a chemical bond. To finish that off, a treatment is normally applied to the materials. And the very last aspect is converting those materials into what we need them to be in our hospital settings, and that's now called conversion, it's known as. Of course, these types of materials can be used for a variety of things. They're used in industry, in all sorts of places, but now let's take it down to what it is we need in our environment. On the left-hand side of our picture over there, you can see the raw materials, and in the middle you'll see the graphic of a piece of equipment that does all of this web formation and bonding process. It's kind of like a hopper system, and on the top hopper, the raw materials are put onto like a conveyor system. The spun melt material popped in, then a melt blown, then a melt blown, then a melt blown, then a spun melt. It depends on the materials, who the manufacturer is, as to what that order is. Maybe it's a spun melt, a melt blown, and a spun melt. It's possible to have it the other way around, MSM. The ones in South Africa that we know are SMMSs and SMSs mostly. And the last part of the process is the actual web formation. On the left, again, here's a bit more of a graphic that helps to describe the materials going through the hopper onto the conveyor belt, as described in the first section of the graphic. The image on the right is a machine in a plant owned by Alstrom, where the actual production occurs. It's a really nice, clean factory, very impressive. The last part, as I referred to, number 2, is the thermal bonding, or the bonding section. And in this particular machine, it uses thermal bonding using calendering. So with calendering, it's a heat and high pressure that's applied through rollers to weld the fiber webs together at high speed. So that's how the materials are then bonded together. Once we've completed the manufacturing, now we need to convert it, and we are now needing to convert it into the product that we need in our hospitals in the South African setting. So the raw material arrives on a ship, on a rather large container, into South Africa. You can see the image of the left of the raw materials as they arrive, stored in the warehouse. The raw material, is then loaded onto a machine that will sheet the material, so cut the wrap into the various sizes that we require. At the conversion facility in Cape Town, SafMed are actually able to interleave the wrap. The image in the middle over there, you can see the 2 different colors of materials. That is interleaving, so putting it into the 2 different colors. The advantage of that, of course, is of an interleaved with 2 different colors, is that it makes it so much easier to see a hole. So if you've got a hole in one layer of the wrap, you can see it quite quickly because of the contrasting color. Some customers actually also like to use a combination of an SMS and a wet-laid non-woven together. And again, the advantage is that can be interleaved in the facility in Cape Town for you, so that the end user, us in the CSSD, don't have to then make the layers of the bed ourselves. It's all ready for you. The sheets are then placed into impervious plastic sleeves, and they're purposefully packed in 2 layers of plastic sleeves, so that when the materials arrive on site at your CSSD, you can remove that outer layering so that you don't carry any external contaminants into your CSSD, and that you then have a nice clean product to use. Of course, to wrap our sets for our patients. Converting into a Aseptor bag, that's also an exciting and interesting process. I've asked Roger, who's on the call today, to please describe that process to us. Roger, if you could.
Thank you.
There you go.
Right. These Aseptor bags are manufactured locally in Cape Town. We have a manufacturing team of about 30 staff members. And of course, SafMed holds the ISO 13485 certification, which includes the process for manufacturing Aseptor bags. The raw materials are used, that are used to manufacture the bags are produced in compliance with the relevant international product standards. For example, the medical grade paper and the sterilization ink used comply with the relevant ISO standard. The bag making process starts with printing, followed by folding, application of the adhesive, and finally the cutting and packaging of the bags. When we run the production of a particular size bag, the machine needs to be set up for the size of the bag. It takes approximately 3 hours to change over from one size to the next. So we need several different bag machines to cater for the various bag sizes. Of course, we have in-process quality control checks, which are performed for every lot number manufactured. These include dimension tests, print test, autoclave test, post-autoclave seal test, ink and paste line test, grammage test, pinhole test, bag burst test, and ink viscosity test. Finally, In addition, SafMed is an accredited FP&M seated training provider and offers 3-year apprenticeships for our bag making diploma. Thanks, Anna.
Thank you very much, Roger. So that's quite amazing that the process happens in our facilities in Cape Town, and we know that we are getting a quality product. In the ISO standard 11607, it clearly states that all converting and all processes need to be performed in a facility that is compliant and has a formal quality management system. Of course, in medical devices, that is 13485. Moving on to EN 868. So we start with 11607 when it comes to sterile barrier systems, and then we go a little deeper into EN 868. And EN 868, as you can see, is divided into from parts 2 to part 10. Part 2 deals specifically with sterilization wrap, part 3 with the paper, part 4 with paper bags, Part 5 with sealable pouches and reels. Part 6, you can see 7 adhesive coating. 8 is containers. 9 is, and 10 is the Tyvek material. So that's the material, of course, we use for vaporized hydrogen peroxide sterilization. So in these particular standards, it goes into greater detail, and it also goes into the actual test methodology as well. I'm going to point to some aspects in 868 Part 2 that fall under Section 4. Some examples. No color shall reach out of the wrap. It must be compliant as tested using a visual examination, and it goes on to describe in the standard how that actual test method is performed. The average mass of the conditioned wrap when tested must be in accordance with the standard and must not be more than 5% out. In other words, if we're telling you a product that says 43 grams or 37 grams, whatever it is, remember I explained last week that wrap is made and is available at different grammages. It has to be as it is advertised, as it is supplied to you. It must weigh what it is we say it must weigh within a 5% tolerance. Another important aspect is the chloride content of wrap. Again, that should not exceed a specified amount, and the standard will define how that testing is done. These are general aspects: the color, the average mass, the pH value, the chloride, the sulfite, the fluorescence. And your supplier must be able to provide you with certification that the materials that you're purchasing does comply with the required outcomes. Of course, it's always useful if that testing methodology has been done in an independent laboratory facility and not just by the manufacturer themselves. Moving on to some more specific based information. When it comes to this part of the standard, it is divided into wrap made of crepe paper, wrap made of paper, wrap made of non-woven materials, etc., and also reference to reusable materials as well in this section of the standard. I took out an extract of the specific requirements for non-woven material, of which SMS is an example. And the reason I did that is because I have some images of the tests being performed on SMS materials that were kindly shared with us from our partners. Important aspects of the barrier material is its tear resistance, and it is measured in different directions. The bursting strength, the hydro head test, and the tensile strength. Important to know that the product that you're using conforms. Here is an image of the tear test. Images supplied, as I had said, kindly from Alstrom, from a test lab facility in France. As you can see, the image on the left, a known defined amount, believe you me, everything is completely defined amount of material is placed into this device. That pendulum is then released, and then a known amount of pressure is forced, so that at the end of the day the wrap will tear. You want it to tear because you're going to define at what point it does tear. You can see the image on the right there. The technician, the laboratory technician, is holding the two pieces, and of course you can set the pressure on this particular device so you know exactly the known amount you are testing for. This is the burst test, and the burst test measures the resistance of a fabric to a burst or a puncture. And this, of course, is important to us, both in the CSD and the operating room. We want to know that our sterile barrier system is doing the job it's meant to do. Looking at the images on the left, a piece of material of sterile barrier system is placed on the platform. A pressure is applied. The pressure is applied from below. If you look at the very last image over there, you can see the hole that has come from the bottom of the material. You can see the hole that is formed purposely with a known amount of pressure again to test at what point it will burst, it will puncture. This test is the Tensile Test, and it measures the ability of the fabric to withstand elongation. So you can see the image over here where a piece of material of sterile barrier system has been placed and then actually pulled in elongated direction. Moving on to, I think, one of my favorite tests. Actually, this one and the hydro head are my two favorite tests. This is about microbial barrier properties. It is very important that a sterile barrier system has microbial barrier properties. So the material itself is the important aspect here. ISO 11607 states that a sterile barrier system needs to provide adequate microbial barrier to microorganisms. In this case, we're referring to the material itself being able to prevent the ingress of microorganisms. And the test methods that is performed to measure this is called the Germ Proofness test. Now, a Germ Proofness test, there are two versions of it. There is a wet test and there is a dry test. And in a laboratory setting, we make use of live microorganisms to perform this testing. And this testing is performed on a piece of sterilization barrier material after sterilization. Important point to bear in mind. So I'm going to describe this method. It's really quite cool because we've got quite a few images of it, and we'll look at some important aspects around it. So we begin with 10 pieces of sterilized wrap are prepared. As you can see, there's defined size that piece of wrap needs to be. Staphylococcus aureus is added to a known amount of water. 5 drops of water are then placed on top of the sterile barrier system that's now been prepared, my 10 little pieces, quite specific, 5 drops. Those drops are then left to dry, again for a designated of time between 6 to 16 hours, and that drying time will depend on the temperature that you use. It is then stored aseptically or under correct conditions. It is left for a period of time. After that, the bottom of the wrap then makes contact with the agar plate for 5 to 6 seconds around that period of time. It is then removed and the agar plate is then incubated. As you know, the agar plate contains growth medium, and now we want to see whether or not any microorganisms grow in that growth medium on that plate. And what we're actually looking for is that there are no colony forming units. So we do not want to see any growth. That's what the standard requires. If there are some colony forming units, then there's a process that is to be followed depending on the defined amount. If you look at the image on the right, that is indeed a lab technician performing some of the tests. The green material is standard cotton linen from South Africa being tested in a facility in France. And on the right is a sterile barrier system that is familiar to all of us. Right, so moving on to the dry test. So the dry test is similar in nature, except it's dry. Okay, so we use a jar. In the bottom of the jar is the media. At the top of the jar is where they will affix a piece of sterile barrier material. That piece of sterile barrier material is inoculated with a solution of Bacillus subtilis in alcohol. So we create a membrane on top of the jar. We put on the microorganisms, and then we have to put the jar through a series of temperature changes to try and get the air to pass. So it encourages the air to pass through the actual membrane that now has the microorganisms on it. And it is then heated. I think it's 50 degrees. It then cooled in a fridge, and then heated again, and then cooled in the fridge. And that process is done 5 times. It's then left to stand for a period of time. And at the end of the day, the nutrient media at the bottom of the jar is then evaluated and tested for any microorganisms. There is a maximum amount of colony-forming units that can be per sample, and per 10 samples overall, a maximum of 15. And then, of course, you will get a result of pass or fail. So that is the germ proofness test, the ability of the sterile barrier system to keep out microorganisms. Here are the test results of the dry and wet conditions germ proofness test of standard cotton linen, crepe, and an SMS of 43 grams. And as you can clearly see, I've described the test method to you already. Textile, standard South African textile. I'm not talking about laminated fabrics or other reusable fabrics. I'm referring to standard cotton textile. Failed the germ proofness test. Right, my next favorite test, the hydro head test, as we spoke about a little earlier. This is how the hydro head test is performed. You'll see the beaker on the left, a piece of, in this case, SMS material was placed in the beaker. Again, a defined amount, a defined size. As you can see, everything is defined in a test method. The beaker is then inverted on this platform. 3 liters of water is poured into the beaker, and the time frame is measured, so the material must withstand the pressure of that water. We don't want to see the water coming through the material. When 3 drops of water have started to appear, then that's the end of the test, because now you are finished and the water is starting to come through. And what you're measuring is what pressure of water can you withstand, the resistance to water. Can the material withstand? Here's a hydro head test being performed on standard cotton linen from South Africa. It was almost impossible, I'd like to say the word, to perform the test. I actually have this in a video format, but unfortunately it's always a little trickier to show the videos. And what happened in this case is, as they poured the water into the beaker, it poured straight through. So there was no way of measuring the pressure it could withstand, because it just poured straight through. So it failed the test, and we couldn't get any measurement because it poured straight through. So comparing the test, obviously, you can see on the left, the SMS is able to hold an amount of pressure of water for a period of time, whereas standard cotton linen cannot hold that at all. So we know that the World Health Organization, along with the standard, of course, goes on to describe sterile barrier systems. And we ask ourselves, based on those guidelines, can standard cotton linen be regarded as a sterile barrier system? Well, for many years in South Africa, we've only had standard cotton linen to use, and in fact all over the world. But we've learned a lot since then. There have been many developments in the materials that are produced, of course, over the years. And we know that our sterile barrier system is supposed to be resistant to penetration by microorganisms, free of holes, free of toxic ingredients, lint-free or low linting, must be able to seal it in a manner that is tamper-proof, and it should provide adequate barriers to particulate matter and fluids. So if we think about sterile barrier systems or cotton linen, standard cotton linen, then let's talk about the fact that there are often defects in our wrap, and defects will render it ineffective. Stained linen is problematic. Is there a repair to the linen that's been done? Are there any holes in the linen? Leslie, the wet laid is a method that's used in the web formation. I think maybe Roger may be able to give us a little bit more explanation, maybe a little later, Roger, if you would like to.
Yeah, I'll just comment now, Leslie. It's wet laid. It just refers to the process of manufacturing sterilization barrier material that's primarily made of cellulose paper, but they have certain additives to it to improve its repellency and drapeability. So it's the addition of the various items, and I think Zana talks about it a little bit. It's the addition of those items, so they call it a wet laid process.
Thank you, Roger. Okay, back to cotton linen as a sterile barrier system. The linting of linen, of course, in that regard, it'll fail as a sterile barrier system. The germ proofness test, we know it fails, and a hydro head test, linen will fail. So please, I'd like you just to consider the fact that if you are using standard cotton linen as one of your layers as a sterile barrier system, then please, I need you to think about the fact that does it actually really comply as a sterile barrier system? A very important thing that we need to consider. Of course, we know sterile barrier systems should be used in 2 layers, depending on what it is we are wrapping or enclosing, and we'll go into that in webinar 3 and webinar 4. So if one of those layers is a layer of linen, please think through that. What does the World Forum for Hospital Sterile Systems have to say? Now, the World Forum for Hospital Sterile Systems has an incredible wealth of knowledge and, of course, a series of guidelines that you can access at any time. Dr. Denis will be discussing these in our Africa Health Congress next week, describing how they came to the formation of these guidelines. And in there, you'll see the point that reusable textiles, the barrier performance of traditional cotton wraps is poor and degrades every time we wash it and every time we sterilize it, that we need to inspect it visually for holes and tears, and of course there's a high risk of human error. Textile particles may pollute both the CSST environment and the sterile areas. Touching on the subject of creating a sterile field in the operating room and using linen and sterile barrier systems. So I'm sure, as you all know, that the trolley, the equipment, the mayo stand or the back table and the patient are all part of the sterile field, as I'm sure you know. Should we be using linen as a trolley drape? Well, in 1990 already, of course, the papers were published that discussed the fact that liquid penetrating textile materials readily transports bacterial cells if they are present, of course. And that wet strike-through is quite common in general surgery and many different types of surgery, and it is possible that substantial quantities of bacteria could be transferred. Should we be using linen as a trolley drape? Should we be using a sterile barrier system as a trolley drape? Again, another important question. We have done that in the past, and it's true. That was our method of draping trolleys, and in many hospital environments, we still do that to this day. Not all over the world. In America and in Europe, of course, they do not use sterile barrier systems to drape trolleys with. The AORN states that materials used for surgical gowns and drapes, and remember the trolley is a drape, it is part of the sterile field, they must be resistant to penetration by blood and other bodily fluids as necessitated by the intended use. And for that very reason, there is a completely different standard that defines the requirements for surgical drapes and gowns. And those requirements are different to that of a sterile barrier system. Take, for example, the hydro head, the resistance to liquid penetration. That needs to be 100 centimeters of water. Generally speaking, out of a sterile barrier system, you might get, depending on the make and the nature and the grammage, maybe 20, 30 centimeters of water out of that. That's not what is required for a trolley drape or a patient drape. So using a sterile barrier system for the wrong person, for the wrong purpose, is a very important thing that we need to think about. The point that I want to conclude with, which is, I think, the main reason for this part of our presentation, is this: the material used to wrap our sets, the material used to wrap our devices and our instruments must conform to the relevant sterile barrier system standard. A sterile barrier system is designed and tested to perform as a sterile barrier, not as a drape. It's designed for a specific purpose. In webinar 3 and 4, we'll talk more along the lines of this terminology about what is a packaging system, what is protective packaging, what do the two layers together do, how do they help us. We'll also look a little bit more at ISO 16775, a really interesting standard that talks about how we actually are meant to be using our sterile barrier systems in the clinical environment. The different methods of folding when we wrap. How do we create the tortuous path when we're wrapping? Are we wrapping correctly? The validation requirements. How do we actually validate that something seals properly once we've assembled it? How do we know that our method is correct, and how do we test that? Including, how do we test reusable containers? How are we supposed to open our packaging, and therefore how do we actually put it together? Are we leaving enough room to grab? Are we using the right tear direction? Are we opening the packaging in the right manner? Should we be drinking and eating in the environment where the systems, the items are being packed? It's all covered in this standard 16775. So we were a little bit quicker than we had planned today. Thank you very much for joining us again. Hopefully you learned something new. As normal, we will be sending out a survey with a few questions, and if you would like a certificate of attendance, please go ahead and complete that. Webinar 1, the recording thereof is available, and as I said, in webinars 3 and 4, we'll go into a lot more detail in terms of how it is we are going to use our sterile barrier systems, or should be using them, in the clinical environment. Thank you very much for joining us today.